right, so we're going to continue looking at section 6.1. So in the first part, we talked about angles. We looked at different names for angles, how we can classify angles based on their size, pairs of angles like complementary, supplementary. And then the last thing, that was the most important thing we did, that was looking at how to convert between degrees and radians. So we're going to start off by looking at a formula in this section called arc length. And this is going to be a formula that only works in radians. Okay, so it's going to assume that your angle you're plugging into the formula is already in radians. If it's not, that's going to be the first step. Change degrees to radians. Okay, so what is an arc? So an arc is basically part of the circumference of a circle. If you had the entire circumference, that's still an arc. It's just an arc that's so big, we usually call it the circumference. Right? So let me draw a couple different arcs. And I want you to notice, hopefully notice something. All right, I'm going to draw an angle inside the first circle. That's 90 degrees. So I have a 90-degree angle. And then the arc made by that 90-degree angle goes from here to there. So that's a picture of a 90-degree angle along with the arc it creates on the circle. All right. Now I'm going to double the size of that angle. Okay, so if I double it, I'm going to have a 180-degree angle. Initial side, terminal side, and that's my arc now. Okay, so here's my question. I doubled the size of the angle. Does everyone agree 180 is double 90? Okay. What happened to the size of the arc? Size of the angle doubled. But how about the size of the arc? Yep. It also doubled, yeah. So there's a direct connection between what we call arc size and angle size. However many times bigger you make the angle in that picture, that's how many times bigger you'll make the arc. If you made the angle half as big, you would make the arc half as big. So there's a direct connection between angle size and arc size, and that's called directly proportional. Not everything works like that. Sometimes if you change one thing, the other thing doesn't change exactly the same way. Right? But in arc size and angle size, they do. They are directly proportional. When two things are directly proportional, it means that we can set up a proportion. So right, that's what we're going to be using in a minute to figure out the formula for arc length. Okay, so I'm going to draw another diagram. And this time I've drawn two angles in the circle. Okay, I don't know the measure of either angle. It's not like it's a 90 or a 180. It's just an angle. I've called the angles theta, but I can't use the same name twice because they could be different angles. So we can call it theta and theta 1. S is the arc that's connected with theta, and S1 is the arc connected with theta 1. Okay, so two different angles, two different arcs. R is the radius in that circle. Okay. So what we need is some kind of connection between arc size and angle size that we already know. Kind of like if I said I want you to convert between miles and feet. Well, in order to do that, you have to already know some fact that connects miles and feet, like 5,280 feet in a mile. Once you know that fact, or any other fact that's true, you can set up a conversion between feet and miles. There's something here that we can use. Okay? When we first talked about the definition of, when we started about radians, I drew a picture of 1 radian. Does anybody remember we can make these two things exactly the same size. The arc and the radius. Right now in this picture, like if you look at this one to scale, I don't think that red arc is the same size as the radius. That angle's a little bit too small to have that happen. It would have to be a little bigger. But my question is, how much bigger? Does anyone remember what this angle right here has to be in order to make this arc and this radius exactly the same? Because if we can figure out the size of the angle that makes those two things the same, then we will have a connection we can use to base everything off of. Kind of like saying in 1 foot, there's 12 inches. That's a fact you can base everything else off of. So how big does this angle have to be to make the arc and the radius the same? Okay, so did anybody figure out how big that angle has to be to make the arc and the radius match? Yeah.
1 radian?
Yeah, it has to be 1 radian. Okay. So let's suppose that angle is 1 radian. Then we know the arc and the radius match. So you might think at first, well, how can you assume it's 1 radian? Well, it's like, how can you assume in 1 foot there's 12 inches? That's a true fact. It's just that's the definition between feet and inches. 1 foot equals 12 inches. It's not an assumption. It's a fact. Same thing with this. This isn't an assumption. This is a fact. In any circle, if you make an angle of 1 radian, then the size of its arc will match the size of the radius in the circle. So we're going to use that fact to help us set up a formula. Okay, so we just figured out that the arc and the angle size are directly proportional. So that means we can set up a proportion. And in our proportion, we're going to have those 4 things that I just circled in blue. Okay. Anybody think they could help me set up a proportion? And there's lots of ways you can do it. Using those 4 things that I just circled in blue. And let's start with just filling out the left side of the proportion. Jade, could you help me fill out the left side, setting up a proportion?
I don't think I can.
You don't think you can help me?
No.
You want to phone a friend?
Yeah.
All right. Who's going to be your lucky phone a friend?
Anyways.
All right, Annalise. Can you help us set up a proportion that is going to involve those 4 things circled in blue, and there's lots of ways you can set up the left-hand side. Take a guess at it. Tell me something you think you could fill in on the left side. Yeah, one of those things circled in blue. Theta, okay. So theta. And what would you put in the bottom?
Over S.
Over S, okay. So we did an angle over an arc. Now you don't have any traces on the right. You have to set it up in the same way. You did an angle over an arc. So on the right side, do another angle over another arc. So anyone think they could fill out the right side now? That's?
Would it be 1 over arc?
Can you fill it in with those things circled in blue?
So 1 radian would be the numerator.
So it either has to be this,
Oh.
this, or that. Those are your 4 choices.
Right.
And I wouldn't pick this or that,
Okay.
because we already used them.
So then S1 would be your denominator,
S1 would be in the denominator, okay?
and theta 1 would be your numerator.
Yeah. So that's a proportion that you could set up that would correctly relate angle size and arc size. They are directly proportional. And now we have a little bit of information we can fill in there. What did you say we could fill in for theta 1?
1 radian.
Yep, we're going to fill in 1 radian. And what would that make my denominator?
That make it R.
It would make it, wait, what'd you say?
R.
R, yeah, it would make it R. So what we just wrote down right here, that's like if you had a formula and you were trying to convert between feet and inches, and you just filled in something that was true on the right-hand side. And 1 foot was 12 inches. That's what we basically just wrote down right here. This right-hand side is a true statement based on the definition that if you have an angle of 1 radian, the arc and the radius match. If you have a length of 1 foot, then it matches to 12 inches. It's the same idea. Right. Now we need to solve this proportion, and the goal is to get S by itself. And then that'll give us a formula for the length of any arc in a circle. How do you solve a proportion? Yeah?
I don't fully know how to explain it, but you have to just like multiply the numerator of one side with the denominator of the other side.
Okay, yep. And there's a name for that. Does anybody remember the name? Yep.
Is it cross multiply?
Yep, you're going to cross multiply. So you're going to do, sorry. You're going to do S times 1. And then you're going to do R times theta. And there you go. So that's an equation for finding the length of an arc in a circle, as long as you know the radius of your circle. That's one thing that controls the size of the arc, and how big of an angle you have. So that's the arc length formula. So S is the length of the arc, R is the radius, and the angle we assumed way back at the beginning of the problem was radians. So you need to make sure you use radians in this formula. Okay, same thing when I wrote down that conversion between feet and inches, that conversion assumed you're using feet. So if you wanted a conversion between miles and kilometers, well, 1 foot equals 12 inches isn't going to do it. That's not the conversion we used. Right? Same thing here. Our conversion used, or our formula used radians, so you have to use radians. So you'll always know 2 out of 3 of the variables when you're finding, when you're using that formula. You could be solving for arc length, you could be solving for radius, or you could be solving for the angle. Any of the 3. All right. So let's find the length of the arc in a circle that has a radius of 2 inches, and the angle inside the circle is pi divided by 4. Now they've drawn a picture and they've given you a description in words. They don't have to do both. Right? Generally, they're only going to give you one, but I'm trying to show you graphically, like as a visual, what you're doing. Okay, you're finding the length of that part in red. All right. What's the first thing that we're going to need to figure this out? Without this, we're not getting very far. Ethan?
Just the formula.
Yeah, we need the formula. Can you tell me the what the formula is?
S equals R times theta.
And can you tell me what the letters stand for?
S is the arc length,
Yep.
R is the radius, and theta is the
Is the angle, yeah. So fill in everything that we know. This time it says find the length of the arc. So we are solving for S. Dario, what's my radius in this problem?
2 inches.
2 inches. So we're going to fill in 2 inches. And what about, Declan, what's my angle?
Pi over 4.
Pi over 4. And what is what's the units on that?
Radians.
Radians. And what units am I supposed to use in my formula?
Radians.
Radians. So I'm all set. Okay. So the length of the arc is 2 times pi over 4. And not as a decimal, just tell me, what is 2 pi over 4 reduced to? Yep.
Pi over 2.
Pi over 2. And because we were finding the length of something, we do need a label on that. What should be my label on the pi over 2? Well, Marin, what's my label on that?
Radian?
Did we find an angle? What were we solving for?
The length of the arc.
We were finding the length of an arc. So if you're not finding an angle, then no, we shouldn't use radians. We were finding how long something is. So what should we use for a label for length?
Was it inches?
In this problem, it was inches. Yep. So the length of that arc is pi over 2 inches, or about 1.57 if you divide it out. Okay. So any question on finding the length of the arc using that formula? Now, if you forgot the formula, another way you could do it is, I guess you could figure out the circumference of the circle and then figure out what percentage of the circumference the arc is taking up. Right? You've got that's a 45-degree angle. What part of a circle is 45 degrees in terms of how much of a revolution it is?
An eighth.
It's an eighth. So if you figured out the circumference of this circle and then you took 1/8 of it, that would give you the same answer. It's just that's a little more thinking, because then you got to figure out the percentage of the circle you're looking at and then multiply it by the circumference, and this is just faster. Right? Let's try this one. Okay, example 6b. So this one's a little different. This time you are not finding the length of the arc. You're finding the length of the radius. All right. So it says the arc length is 3 pi feet, and the central angle is 60 degrees. Evan, what's the first thing I'm going to need to figure this out?
Formula.
Yep. And what's my formula that connects radius, central angle, and arc length?
Well, you just want me to fill the numbers in?
You don't even have to fill them in yet.
Just S equals R times theta.
Yep. S equals R times theta. Now, can you tell me which numbers are going to go where?
So S is 3 pi.
This time the S is 3 pi, yep.
R is just going to stay.
R stays, because that's what you're solving for.
And then you have to turn 60 into radians.
Right. We can't fill in that 60 degrees the way it is, because we have to convert it to radians. And what do you get when you convert 60 degrees to radians? Yep.
Pi over 3.
Pi over 3. If you multiply by pi and divide by 180, 60 goes into 180 3 times. Okay. All right, so now we got to get R by itself. How about, Layla, how can I get R by itself there?
You would multiply that
Mhm.
by its reciprocal.
Yep, and what's the reciprocal?
3 over pi.
Yep, perfect. So multiply each side by 3 over pi. Pi's cancel. And what am I going to get for my final answer here? Yep.
9.
Can you give me a little bit more information?
Not yet.
Yep.
9 feet.
9 feet. So anytime you're solving for R, it should have a label like inches or feet or centimeters. Anytime you're solving for S, it should have the same kind of label. If you were solving for the angle, you should put that in radians. But you don't need to write RAD, because we don't write it. question on that? Okay, so remember, this formula always gives you an answer in radians if you're solving for the angle, or if you're plugging in the angle, it has to be in radians. Okay? If you wanted something in degrees with this formula, well, you'd have to do this out, and then if you were solving for the angle, you could change it yourself to degrees after. But whenever you plug something in, it has to be in radians, and the answer you always get is in radians for the angle. Length units can be anything you want. Feet, inches, that doesn't matter. Okay. Any questions on that? So that's the arc length formula. All right, so last thing we're going to take a look at is what's called angular velocity. Well, what's velocity? What is that? See the word like velocity. How would you explain what velocity means? That's
It would be like the speed and direction of objects.
yeah, it's the speed and direction of an object. Now, angular is measuring the speed and direction of an object, but what kind of speed do you think it's measuring? It's not measuring like the speed, you know, like if someone was on the side of the road and had a radar gun and watched your car go by. That's linear speed. It's going straight. What do you think angular speed measures? Yeah? Rotation, right? Something spinning, RPMs. Right. So sometimes you look at power tools, they're rated in RPMs, like how many revolutions per minute they spin at. Your car, some cars have like a tachometer, and it tells you how many RPMs the engine is running at. So we're measuring something moving on a circular path. Now, angular, there's really two different ways we measure angles, degrees and radians. We're going to generally be sticking with radians. So if in the book you don't see any directions on what labels to use, I always want you to use radians per whatever time unit you want. It can be radians per minute, radians per second, radians per day, but we're going to stick with radians, unless the problem specifically said use degrees. All right, so let's take a look at this. And I want to look at this picture. And I want to first just remember, what's the formula for distance? Distance equals, I think we might have talked about it at some point. Yeah?
Is it rate times time?
Yeah, I think we did it when we talked about like a train problem and somebody was traveling by car and train at one point. But yeah, distance equals rate times time. So what I want to do is I want to spin that disk, and I want to look at the three dots, the black, the red, and the green. And I want to describe how fast each dot is moving. Okay, so I'm going to make one revolution, go all the way around one time. And what do you notice as I go around one time? Any observations of those three dots? Yeah?
Origin doesn't move.
Yeah, it looks like the black one didn't move at all, right? It just stayed, you know, it's not perfect, but it pretty much stayed right where it was. Well, if the distance that something travels is 0, how fast is it going? Yeah? 0. So it's like that black dot had a speed of 0, right? What about the red and the green dots? What do you notice about those? Yep.
They're moving at the same speed.
How about, can you describe how far they each moved? if I just rotate it one time, how would you compare how far they've moved? They each moved the same distance? So like, as they moved, what path did they trace? Like if you were to, like if it was like a marker and it was actually being dragged, it would draw a what? Yeah, it would draw a circle. So if they each move the same distance, then you're saying the red dot and the green dot would each be the same size circle? Yeah.
The red dot and the green dot would make a different size circle, so the green would have to be going faster.
Yeah, the green dot is definitely traveling farther than the red dot, right? If you were to walk on the path created by the circle for each dot, the green one is traveling farther. Now, if you compare the time, they're each doing their circle in the same amount of time, right? However long it takes the red one to do its circle, it's taking the green one exactly the same amount of time. So if the green one is traveling farther in the same amount of time as the red one, then what does that mean about the green one? Yeah?
It's going faster.
It's going faster. That's a problem. So now if we want to describe the speed that this entire disk is spinning at, then how do you describe it? Do you have to say, well, if you were standing on this part of the disk, it would be going at this speed, but then if you were standing right in the middle, the disk has no speed, right? It starts to get kind of confusing. So that's why when we describe something spinning, we don't try to describe it using a concept like that, okay? Because every point along the disk, from the center to the edge, would be spinning, would be traveling at a different linear speed. So what we're going to do instead is describe the speed of this disk angularly, which describes how many revolutions the dots make per minute, not the length of the path that the dot is traveling. Okay? Every dot on this circle is making one revolution, and maybe it took me like 4 seconds to go all the way around. So they're all traveling at 1 revolution per 4 seconds. Right? And they're all traveling at the same angular speed. So angular speed will always be measured in radians per whatever time unit the problem gives you. Now if you compare that to linear speed, right, that's what we're more used to measuring, and that's like what your car tells you. It says, 60 miles per hour. That's in a straight direction. That's not telling you how many times your tires are spinning per minute. That's a different number. Most of the time, we don't care how many revolutions our tires are making per minute. If you get pulled over for speeding, you're not going to be told, oh, your tires were going 300 revolutions per minute. You're going to be told you were going a certain miles per hour. Okay? So that's linear speed. So linear speed can use any length unit that measures distance, feet, inches, centimeters, kilometers, divided by any time unit. So with linear speed, we have a lot more options for the units. With angular speed, the only two that we have are radians and degrees, and we're always going to stick with radians. So we're a lot more limited with the units that we can pick from. And the way that we're going to convert between angular speed, linear speed, and all these conversions we're going to do is all looking at the dimensions. It's the same way I just showed you how to convert between radians and degrees. If you've got a unit in the top of a fraction and you don't want that unit, then you need to put it in the bottom of another fraction. Okay, so that's how we're going to figure out our conversions. Okay, by looking at where the units are we want to cancel and making sure they're in the opposite spots. Basic conversions you do need to know. All right, so conversions like how many seconds in a minute, minutes in an hour, hours in a day, days in a year. I would expect you to know all those. Basic length conversions, how many inches in a foot, feet in a yard, feet in a mile. Okay, those you should know. Something like how many inches in a kilometer? No, I wouldn't expect you to know that. That's not a standard conversion. All right, so we're going to start by not even looking at a speed. Okay, this isn't speed. This is just time. And I just want to practice doing the dimensional analysis. I want to convert 3 days into minutes. So we're going to multiply by different fractions as we go. And the first unit I want to cancel out is days. So I need a connection between days and another unit that's going to get me towards minutes. I'd like to go 1 unit at a time. So I don't want to jump all the way from like days to minutes. There's a unit in between. Yep.
1 day is 24 hours.
Okay, and if we're trying to cancel out days to get, it would go on the bottom. And you said 1 day is 24 hours. Yep. So now, because we have days in the bottom, days in the top, it cancels out. That's the idea of dimensional analysis. All right. Now we want to cancel out hours. So now I need another conversion that's going to connect hours, and we can go right to minutes now. We don't have to go to, there's no unit in between that we need. Yep.
So 1 hour apart.
So 1 hour on the bottom. That's the connection between hours and minutes. It's a 1 to 60. And then we're going to cancel out hours. And now we multiply. If you want to think of this as a fraction, you can just put a 1 over it. You multiply straight across. Sometimes you end up with all 1s in the denominator. Sometimes you don't. So just multiply straight. So 3 times 24 times 60 gives you 4,320 minutes. Okay, and again, the point there wasn't really to convert between days and minutes. It was to analyze the units as we go to show you how they cancel out. Now, this particular problem only had 1 unit in it. It was just minutes. Okay, the next problem is going to have 2 units. It's going to have a length unit and a time unit. Okay, so now we're dealing with a velocity. We're dealing with a speed now. 50 feet per 1 second. And I want to convert that to miles per hour. So 50 feet per second means you travel 50 feet in 1 second. So now this is really 2 problems. We've got to get the length unit to miles, and we have to get the time unit to hours. It doesn't matter which one we do first. All right. Let's do the time unit first. Okay. We try to go 1 unit at a time without skipping a unit in between. Okay. We're trying to get seconds to hours. So what unit are we going to go through to do that? Yep.
60 seconds.
So yeah, there's 60 seconds in 1 minute. So we need the 60 over 1 because we want seconds to cancel out. Now we want to get rid of minutes and go to hours. So what would be my next conversion to get me to hours? Yep.
60 minutes and 1 hour.
There are 60 minutes in 1 hour. So now if you look at what you have, seconds is gone, minutes is gone. You have a speed in feet per hour if you did that out. Okay, but we don't want feet, we want miles. Even if you don't know the conversion numerically, you should know where feet is going to go in that fraction. Where's feet going to go in this last fraction? Yep.
On top.
Why on the top?
Because you don't want to cancel out.
We do want it to cancel
Oh, it's
out.
still done.
So we want it on the bottom because it's already in the top. So we're going to put feet in the bottom. And what unit would be in the top?
Miles.
Miles. Okay, so you've got your labels set up right. But now you need the conversion. What's the connection between miles and feet? Yeah.
It's 5,280 feet per mile.
1 mile. Yep. So feet and feet. This time we did not end up with all ones in the denominator. So we're going to multiply everything in the top together and then divide by 5,280. So 60 times 60 is 3,600 times 50, and then divide by 5,280. So if something's traveling at 50 feet per second, that's 34.09 miles per hour. I would say generally we're going to stick with an abbreviation like miles and then slash hours rather than mph, just because it clearly shows miles is in the top of the fraction, hours is in the bottom, miles per hour. Okay, any question on that? So let's try another one of those. Okay. But this time, this was a linear speed to a linear speed. Right? Feet measures straight distance, miles measures straight distance. So linear to linear. This is angular to angular. Radians measures something angular, and revolutions can also be used to measure something that's rotating. So it's angular to angular. So it's 200 radians per 1 second. Okay. Can somebody give me my first conversion? You get a couple options. To try to start getting 200 radians per second into revolutions per minute. Look, Marcelo, can you help us out?
Will I turn the seconds to minutes?
Sure, if you want to.
You put 60 seconds in 1 minute.
Yeah, so there's 60 seconds in 1 minute, and if you stop there, what would your label be on your problem now?
Radians a minute.
You'd have radians per minute. Yep. Well, we don't want radians. We don't want radians per minute. We want revolutions per minute. So we still have one more thing we have to fix. What's my next conversion going to be? Yep.
1 revolution over 2 pi radians.
Yep. In 1 revolution, there are 2 pi radians. Radians in the top, radians in the bottom. Now if I multiply straight across, I have revolutions in the top, minutes in the bottom, and that's what I wanted. Okay. But we stuck with angular the whole time. We started in angular, we ended in angular. The one before started in linear, ended in linear. Okay, let's see what we get now. So we get 200 times 60, so there's your numerator. And we're going to divide by 2 pi. You do want to put parentheses around that 2 pi. That's the correct answer. If you don't, let's take 12,000 and let's divide it by 2 pi. What did it do there? That's wrong. Yeah?
It just divided it by 2 and then multiplied by pi.
Right. It divided 12,000 by 2 and got 6,000. And then it did 6,000 times 3.14. And that's how it got 18,000 something. All right. So you've got to make sure if you want to do it like I did, all in one step, you put that 2 pi in parentheses. So 1909.86. And that's revolutions per minute. Okay. Any question on that one? All right, let's try this one. So it says that we have a wheel with a radius of 18 inches rotating at 1,850. I did use a 3-letter abbreviation there. If you weren't sure what RPM stood for, that I would tell you. That stands for revolutions per minute. All right, so part A, find the angular speed of the wheel in radians per second. Okay, so what's the speed that they gave me of this wheel to start with? Lens?
1,850 revolutions per minute.
Right, 1,850 revolutions per minute. That 18, I don't need that right now. Right, that doesn't have anything to do with angular speed. I know the speed is 1850. All right, so let's write that down. 1850 revolutions per minute, and our goal is to end up with radians per second. Okay, can somebody give me my first conversion to get the revolutions per minute into radians per second? Yep, Dr.
1 minute over 60 seconds.
In 1 minute, there are 60 seconds. Yep, perfect. And I need one more conversion. Yeah, Jackson.
2 pi radians over 1 revolution.
2 pi radians in 1 revolution. There you go. So now we just multiply straight across, and we have our radians per second. All right, so we've got 1850 times 2 pi. You don't need parentheses around the 2 pi there because there's no division happening. It's just going to multiply straight across, and it'll handle that fine. And when you divide by 60, that's just a single factor, so you don't need parentheses there either. So it's 193.73. And that's radians per second. All right, nothing that different about that one. It's pretty much what we did in example 7C. Actually, just in reverse. We did radians per second to revs per minute, and this was revs per minute to radians per second. All right, let's look at part B. What's different about part B? We haven't not done one like part B yet. Yeah.
He's asking for linear speed instead of like angular.
Okay, well, we did do linear up here in 7B.
It's like angular to linear.
Yeah, it's angular to linear. It's a conversion from one type of speed measurement to another. Okay? So the way you can visualize what's happening here is imagine that you had like a tire spinning on a machine at 1,850 RPMs, and all of a sudden the tire fell off the machine, hit the ground upright, and then started rolling. That speed that it was spinning at is instantly going to be converted into linear speed. That's basically what we're figuring out. If this tire hit the ground at that revolutions per minute, how fast would it be rolling? Or what would it be its linear speed? Right? All right, so whenever you want to convert between angular and linear, you need to be in revolutions. So part A actually didn't help us to do part B at all. Right? It was just a separate question they wanted us to do. So to convert between angular and linear, you need to be in revolutions. That's what was given to us. So let's go back to that. 1850 revolutions in 1 minute. Well, they want seconds, so we can convert that again. That part's straightforward. In 1 minute, there's 60 seconds. Okay, so now we're back to revolutions per second. In the next conversion, what unit do I want to try to get rid of? Yep. I want to get rid of revolutions now. So where would that go? It would go in the bottom. Now, eventually I want to get to feet. But what linear unit did they give me in the problem to work with? Yep.
Inches.
Inches, okay? So then I'm going to go to inches first. This conversion is asking you how many inches in a revolution? How many inches in one revolution? Yeah?
12 inches.
12 inches? How about when the Earth revolves around the sun? Pretend it was circular. Is that 12 inches? Not quite. So how many inches in one revolution? Yeah.
36 pi.
Can you explain more about that?
I was thinking of the circumference, like the 2 pi r.
Okay, so we do have to do something with circumference, but in general, how many inches in any revolution? Why is that a tricky question to answer? If someone said, how many inches in a revolution? Why isn't it like asking you how many inches in a foot? That's a different kind of question.
Because it depends on what you're going to do.
Right, it depends on what you're revolving around. Right? So how many inches in a revolution, you need to calculate that conversion every time. It's not a conversion you could just look up, like feet to inches, seconds to minutes, things like that. And Jackson, how did you figure out how many inches in a revolution?
For the circumference, like radius to circumference, I did the 2 pi r.
Yep, so circumference equals 2 pi r, because a circumference is a revolution. So if we can figure out how many inches in a circumference, that tells you how many inches in a revolution. And what was our radius in this problem? Yep.
18 inches.
18 inches. So that's 36 pi inches in this particular revolution. Not in every revolution, but this one. So 36 pi inches in one revolution. And that conversion right there just made the jump from angular to linear. Now after that red box, we're in linear now. We're no longer angular. All right? So now we've got inches per second. And we want to now get rid of what unit there? Yep,
Inches.
inches. And what unit are we trying to get to? Feet. There are 12 inches in 1 foot. I guess you also could have converted the 18 inches right away to feet. You just said 18 inches is 1.5 feet. But this way works fine. Okay. So let's do this out. So we've got 1850 times 36 pi. Okay, so there's my numerator, and we're going to divide by 60 times 12. So divided by 60 times 12. So that's 290 point, we'll say 290.6. And that's feet in the top, seconds in the bottom. Okay. Now, just to get an idea of how fast that is, we converted between feet and seconds somewhere else. When we had 50 feet per second, that was 34 miles an hour. This is 290 feet per second. So that's almost 6 times faster than 50 feet per second. So if you multiply 34 times 6, you're over 200 miles an hour, right? So if an object that size was rotating at 1850 RPMs, like on a machine, and it fell off, and you were standing in its way, you're probably not getting out of the way. It's coming at you a little too fast. Right? So it's 290 feet. I mean, imagine that. That's basically like the length of a football field is 300 feet. So that's a football field in a second. So unless you had like 10 football fields between you and the object, then maybe you could get out of the way. But one football field, 1 second to get out of the way, probably not. Okay, so any questions on that? All right, so that's the two topics for today, the arc length and angular velocity. So homework for tonight is just page 324. The second part on the bottom, we're going to do that tomorrow night. But we'll do 56 to 61 and 70 to 73. Okay. They are word problems with the angular and linear velocity stuff, so that's why there's only 4 of them. And then 56 to 61, that's arc length. Those are arc length.